Hey guys, welcome back to a new video. In this session, we'll be solving integrals using the goniometric substitution methods. These types of integrals are arguably the most difficult ones to solve. Because there's no fixed method of solving them, you need to rely on your feeling and intuition, which you build by experience. That is why, for this topic in particular, the best way to improve is to do a lot of exercises, which is what we will be doing in this and the upcoming videos. As always, the exercises will start out very basic to get an idea of how to approach them, and they will get progressively more complex towards the end. The timestamps can be found in the comment section below, which is of course also the place to share any question, remarks, or suggestions for future topics. And with that, let's get into it. The first exercise that we'll be solving is the exercise where we solve the integral of the cosine squared of x dx. And even though this might look like a very straightforward integral, it is actually not a basic integral, meaning that we cannot solve it in one step. There are other ways of solving this integral, for example, by partial integration. However, in this video, we will focus on solving integrals using goniometric substitutions. And why do we do these substitutions? Well, the goal is to reduce the integrals that we have to integrals which we already know the solution of, so the basic integrals. And for goniometric formulas, these basic integrals are the integral of the cosine of x and the integral of the sine of x. So the overarching goal in any of the exercises that we will solve is to try and reduce the integral that we have to basic integrals of which we already know the solution. In this first exercise, we use the formula that the cosine of 2 times x is equal to 2 times the cosine squared of x minus 1. And we see that this formula connects the cosine squared of an angle to simply the cosine of double that angle. And we can simply rewrite or rearrange this formula in order to get that the cosine squared of x is equal to the cosine of 2 times x plus 1 divided by 2. And this is exactly a formula that we can use in this integral, because we reduce the cosine squared of x, of which we do not know the integral, to a function with the cosine of x, well, 2x in this case, but this can be easily resolved by using substitution. So we get that our integral becomes the integral of the cosine of 2x plus 1 divided by 2 dx. And this can of course be written as the sum of two integrals. The 1/2 is pulled in front of the integral because it is a constant. We've got the integral of the cosine of 2 times x dx plus 1/2 times the integral of dx. And now we have indeed reduced our original integral to two integrals of which we already know the solution. And we can actually solve this first integral using the method of substitution. So we get 1/2 times the integral of the cosine of 2x times 1/2, which is a compensation factor for writing d of 2x. And this 2 here that we plugged in is simply cancelled by this 1/2 in front of it, plus 1/2 times the integral of simply dx. And this we can now very easily solve. We get 1/4 times the integral of the cosine of u du, where u is now equal to 2x, plus 1/2 times the integral of dx, which is of course equal to 1 divided by 4 times the sine of u, because the integral of the cosine of u is equal to the sine of u, plus 1/2 times x, plus a constant c because we're doing indefinite integrals. And at this point we're not done quite yet, because we still have a solution with the substitution parameter u. So we can still rewrite this as 1/4 times the sine of u, and we know that u is equal to 2x, plus 1/2 times x plus c. And this is our final result for the integral of the cosine squared of x. Let's now go to the next exercise, which is how to solve the integral of the tangent of x dx. And contrary to what many people would initially think, this is actually not a basic integral, meaning that we don't know the solution in one step. Or said differently, there is no function that comes to mind such that if we derive that function, that we would get the tangent of x. And therefore, we'll have to do some work in order to solve this integral. The first step of solving this integral is to write the tangent of x as the sine of x divided by the cosine of x, which is basically the definition of the tangent of x. And at this point, we look at this integral and we see that the numerator is actually minus the derivative of the denominator. Because if we derive the cosine of x, we actually get minus the sine of x. And we can write this in the following way. We have the integral of minus d of the cosine of x divided by the cosine of x. And again, what we did here is that we have written the sine of x dx as minus d of the cosine of x. And if we now substitute the cosine of x being equal to u, just rewriting it, we get minus the integral of du over u. And this now is exactly a basic integral, because we know that the integral of 1 over u du is simply equal to the logarithm of the absolute value of u, plus of course the c that we should not forget. And we can rewrite this even further now by resubstituting the cosine of x for u. So we get minus the logarithm of the absolute value of the cosine of x plus c. And to write this result even prettier, we use the fact that the logarithm of x with a minus sign in front is equal to the logarithm of 1 over x. And we can use this to write our final result being the logarithm of the absolute value of 1 over the cosine of x plus c. And this is our final result. And this brings us already to the third exercise, which will be quite more involved. It's the integral of 1 over the cosine of x dx. And here we will use another very common strategy for solving integrals with goniometric functions. This method basically acknowledges that we are much better at solving integrals without goniometric functions inside them than with goniometric functions. So a good way to approach integrals with goniometric functions is to actually try to rewrite them such that there are no more goniometric functions inside of the integral. And oftentimes what prevents us from doing this is that this x in the differential of the integral is not a goniometric function. So we have dx here, but in the integral itself we have the cosine of x. However, what we saw in a previous exercise is that, for example, we can write the cosine of x dx as simply d of the sine of x. And in this way we can rewrite the dx of our integral, which prevents us from getting rid of the goniometric functions, as d of a goniometric function. And what we're left then to do is simply to substitute the goniometric function that we're looking at. And then we simply get dt. So let's see how this works in our exercise that we have here. The first step is to multiply our fraction with both cosine of x in the denominator and in the numerator. So basically what we've done is we've multiplied by 1, but simply we've written 1 as the cosine of x divided by the cosine of x. And then we get this integral right here. And now we see that we can use this trick because we have cosine of x dx in the numerator, which we can now rewrite as d of the sine of x. So let's rewrite cosine of x dx as d of the sine of x. And of course, we should not forget that in the denominator we have the cosine squared of x. And at this point, we're still not there quite yet, because we see that in the differential of our integral, we have the sine of x. However, as the function inside of our integral, we have a cosine squared of x. It would be nice to have a sine of x instead of a cosine of x. However, we know how to write the cosine squared of x as a function of the sine squared of x. We simply use the formula that the cosine squared of x plus the sine squared of x is equal to 1, which is the most basic formula for goniometry. So we get the integral of d of the sine of x, so our differential, divided by 1 minus the sine squared of x. And at this point, we are where we want to be, because in the differential of our integral, we have the sine of x, and the function inside our integral itself also is a function of the sine of x, in this case, the sine squared of x. So what we do now is we do a substitution. We say that t is equal to the sine of x. And this means that we can rewrite our integral in the following way. We have dt divided by 1 minus t squared. And this is now an integral where there is no goniometric function to be found. Well, of course, it is this t, but the form of this integral is not a goniometric integral, and we're much more at ease with solving them. In this case, we can solve this integral quite easily using the method of partial fractions, on which I have recently made a detailed video. The first step of partial fractions is to rewrite the denominator of our fraction. In this case, this is very easily done. We simply rewrite it as 1 minus t times 1 plus t. And the entire idea behind the method of partial fractions is to write the original fraction with a product in the denominator as the sum of two fractions where each of the denominator is one term of our original product. However, now of course, we need to know what will come in the enumerators. We simply write it as a and b. And of course, what we now are left to do is to find a value for a and b. And to do this, we simply write this sum again as one fraction. So we have this denominator times a. So we have a times 1 plus t plus this denominator times b. So we have b times 1 minus t divided by the product of our two denominators, which is, of course, the same product as we had in the beginning. And what we do now is to rewrite our enumerator by grouping all the terms with a t and all the terms without a t. So for the terms with a t, we have a times t plus b times minus t. And so we get a minus b times t. And for all the terms without a t, we have a times 1 and b times 1. So this simply becomes plus a plus b. And of course, we still have the same denominator, 1 minus t and 1 plus t. And at this point, we can directly compare our original fraction that we had, so the fraction of which we have to solve the integral, and the fraction where we have an expression with a and b. And comparing these two, we can find an expression for a and b. Comparing the terms with a t, we see that we have a minus b here, and we don't have a t in our original fraction, which means a 0. So we get that a minus b has to be equal to 0. Now comparing the terms without a t, a plus b here, and 1 in our original fraction. This means that a plus b is equal to 0. And if this all is going a bit too fast for you, I refer you again to this video where I go into detail step by step on exercises about partial fractions. This first equation shows us that a is equal to b. And filling this in our second equation, we get that 2a is equal to 1, or that a is of course equal to 1/2. And that's our first number. Of course, because a is equal to b, this directly gives us that b is also equal to 1/2. And we found our a and our b, which we can now fill in the sum of two fractions, which is equivalent to our original fraction. And we can then solve the integral that we had to solve. So the third and final step is of course to solve the integral of 1/2 divided by 1 minus t plus 1/2 divided by 1 plus t. And of course we have dt here and put some brackets to avoid any confusion. This integral can of course be split into two. So first we have the integral with a 1/2 in front of it, because these are just constant terms, which can always be put in front of the integral. 1 divided by 1 minus t dt plus 1/2, times the integral of 1 over 1 plus t dt, which is simply this integral. And now we are practically done, because we can simply solve these two integrals by using the method of substitution and knowing that the integral of 1 over u du is of course the logarithm of u. So let's do that right away. So we get 1/2 times the integral of minus 1 over 1 minus t d of 1 minus t. And why this minus 1? Well, because we've substituted t to 1 minus t, and this minus sign needs to be taken into account. Plus 1 over 2 times the integral of 1 over 1 plus t d of 1 plus t. And in this case, there doesn't need to be a minus sign, because we simply substituted t for 1 plus t, which simply becomes t again. Which means that we get minus 1/2 times the logarithm of 1 minus t plus 1/2 times the logarithm of 1 plus t, plus c, of course, which is often forgotten. And at this point, you might think that we're already done, but that's not entirely true, because we have to remind ourselves that we are doing exercises on goniometric integrals. And this t that we have here in our solution simply comes from our substitution that we did at the start. We see that t is equal to the sine of x, and that's how we got this integral in the first place. So what we do then now is we substitute t again for being the sine of x. And what we get is equal to minus 1/2 times the logarithm of 1 minus the sine of x plus 1/2 times the logarithm of 1 plus the sine of x, plus c, of course, never to be forgotten. And at this point, we again use a property of the logarithm that says that the logarithm of a minus the logarithm of b is equal to the logarithm of a divided by b. And we see that we can use this property right here. So we get 1/2 times the logarithm of the absolute value of this one, so 1 plus sine of x, divided by the logarithm with a minus sign in front of it, so 1 minus the sine of x. And if we want to get really fancy, we can of course again use the fact that 1/2 times the logarithm of a is equal to the logarithm of the square root of a. And we get our final result, that the integral of 1 over the cosine of x, in case you've forgotten which integral we initially set out to solve, is equal to the logarithm of the absolute value of the square root of 1 plus the sine of x divided by 1 minus the sine of x. And of course, we should not forget this c. And in this case, we see that something that seems to be quite straightforward, the integral of 1 divided by cosine, is actually a quite complicated function, which is inherent to how integration works. Let's now go to the fourth and final exercise, which is where we have to calculate the integral of the sine of 4 times x times the cosine of 3 times x dx. And again, the same strategy applies. We see that we have here a product of a cosine and a sine, of which we don't really know how to solve it. However, we do know how to solve the integral of the sine of x and the integral of the cosine of x. So what we would try to do is to write this product of cosine and sine as some sort of sum of a sine and a cosine, or a sum of two sines. And this is exactly what Simpson's formulas do. And in particular, we have this formula that says that the sine of any number times x, in this case m times x, times the cosine of n times x, so the product of a sine and a cosine, is equal to 1/2 times the sine of m times x minus n times x plus the sine of m times x plus n times x. And we see here that we write this product of a cosine and a sine as the sum of two sines. And this is exactly what we want to do. And it is in this sense that we rewrite complicated combinations, for example, products of goniometric functions, as sums or differences of basic goniometric functions of which we know the integral. So let's now apply Simpson's formula in our specific case. And in our specific case, m is equal to 4, because we have the sine of 4x, and we know that n is equal to 3, because we have the cosine of 3x, which means that we have 4 here, 3 here, 4 here, and 3 here. So our integral becomes 1/2 times, first we have this term, which becomes the sine of 4x minus 3x, plus our second term, which becomes the sine of 4x plus 3x. Close the brackets and we have dx. This integral can then be rewritten 1/2 times the integral of the sine of x dx, because 4x minus 3x is simply x, plus 1/2 times the integral of the sine of 7x dx, because 4x plus 3x is of course 7x. And these two integrals can now very easily be solved. So we have 1/2 times minus the cosine of x, because the integral of the sine of x is minus the cosine of x, plus 1/2 times the integral of the sine of 7x times 1/7 d of 7x. And this is basically a very quick substitution method. So we get minus 1/2 times the cosine of x plus 1/14 times minus the cosine of 7x. And we can rewrite this to get the solution minus 1/2 times the cosine of x minus 1/14 times the cosine of 7x plus c. And this is our result for our initial integral. This brings us to the end of this video. And if you've made it this far, I am of course very proud of you. However, 4 exercises on this topic is not nearly enough to master it. This is why I will be uploading more videos in the future on how to solve these particular integrals and more generally other integrals. So stay tuned for that. If you enjoyed this video, give it a like. And if you want to get notified by these future videos, consider subscribing. And with that, I thank you for watching and I will see you guys in the next one. Bye.